Hello, welcome back. We're continuing our discussion of the Milky Way galaxy, and it's time to think about what the Milky Way galaxy looks like in other wavelengths other than visible light. So let's start, oh, that's not the right tab. We'll get there in a minute. Let's start with the visible. We've already seen what the Milky Way galaxy looks like in the visible part of the spectrum. Looks like again, you got a disk, you got lots of patchy stuff, and you got a halo and a bulge in the middle. What does it look like in other wavelengths? Well, let's think about infrared first. This is I'm about to click the infrared 1 to 4, and that looks like a U, but it's actually supposed to be the Greek letter mu from micrometers. So this is the near infrared. Visible is from about 0.4 to 0.7 micrometers. This is just beyond that. So we're still in infrared seeing the surfaces of stars. But if you remember from our star forming unit, infrared light passes much more easily through these dark clouds than visible light does. So in the infrared, we should see still where the stars are in the galaxy, but we should get it unobstructed, less obstructed anyway, by these very dark clouds. Let's see what that looks like. Ooh, nice, right? Now you can clearly see there's a bulge in the middle. You can clearly see a very well-defined disk structure, and a lot of that very dark just stuff just goes away. It kind of looks a little bit red here now. And so what if we go to further in the infrared? Now this is way in the infrared, 60 to 100 microns. This is way out. We're no longer seeing the stars here in the far infrared. We're going to be seeing here instead the hot, not hot gas, but the gas that's glowing a little bit in the interstellar medium. And so if we click on this one, whoa! Look at the bulge goes away. Interesting. There's no hot gas in the bulge. And look at how thin this distribution of material is. This is the hot gas in the Milky Way galaxy. And look at how much thinner it is than the distribution of stars in the galaxy. Astronomers will sometimes refer to this as the thick disk, and this is the thin disk. The stars are in the thick disk, and this gas stuff, where you're forming new stars, is in the thin disk. If you go out to the radio, this is a particular band that tells us where the molecule carbon monoxide is. It has to be very cold in order for you to get this molecule. But when you do get this molecule carbon monoxide forming, it can emit radiation in a very specific wavelength. If we look at that wavelength in the infrared, we get this view. Again, a very thin disk. The bulge just disappears, but we've got some interesting features that you can see rising up above the disk of the galaxy, but most of it is confined again to this very thin disk of the galaxy itself. 21 centimeters is an important and interesting, again, this is a radial line, but 21 centimeters specifically, this is the wavelength of photons in the radio, comes from neutral hydrogen. So you might ask, remember our energy levels and how hydrogen can emit wave photons is by jumping from one energy state to another. But this one particularly, the 21 centimeters, is a very, very low energy photon. It's a very long wavelength, a very low energy photon. And this comes from two very close states in the ground state of hydrogen. So if you have a cold hydrogen atom sitting there, it turns out that there's two states. Here's some dropping some knowledge about atoms. The proton in the center of a hydrogen atom can have two spin polarities. We call it up and down. And the electron can have two spin polarities. We call it up and down. It turns out that the energy of a spin up electron proton pair is a little bit different than the energy of a spin up proton pair. And if you go from, you can spontaneously flip between the two. And if you have just neutral hydrogen sitting there in the interstellar medium that's very cold, it can spontaneously emit a photon of 21 centimeters. And that's what we're looking at here. This maps out the cold hydrogen in the galaxy. And you can see it follows and maps along quite well with, oh, no, we're not there yet. This is the radio hydrogen 21 centimeter mission. Again, maps beautifully out the very thin disk of the Milky Way galaxy itself. That's where the cold hydrogen gas is. That's where we expect star formation will be beginning. Okay. Interestingly, we go down to the X-ray and gamma rays. These are very high energy photons now, right? X-rays, if I click on the X-ray, you'll see the Milky Way galaxy itself is now dark, and you're seeing, what you're seeing? You're seeing individual bright spots in X-ray. Maybe these are neutron stars. Maybe these are X-ray binaries where matter is falling into a black hole. Very energetic and interesting and unique phenomenon. But you also see some interesting features like this guy coming off here. So the galaxy itself is producing these X-rays as well as the things in the galaxy. And in gamma rays, or even higher energy photons, these are, believe it or not, confined to the disk of the galaxy also. And these are usually come from collisions of very high, called high energy cosmic ray particles that are probably accelerated from supernovae. And when those particles hit these new cold hydrogen atoms in the disk of the galaxy, they can emit gamma rays. And that's where those come from. Cool. Let's go back to our slideshow. Okay, so here's back to our visible light image of the Milky Way galaxy. Again, interestingly, all of the gas, and you know it requires gas to make stars, all of that is located in the disk of the galaxy, and none of it is in the halo of the galaxy. All of the present star formation that's happening in the Milky Way galaxy is all happening in the disk of the galaxy. There is none in the bulge. You notice there was no apparent thickening of the disk in terms of neutral hydrogen in the center of our galaxy near the bulge. It just basically was a straight line all the way across, and there was nothing in the halo. And that means that all the star formation is happening in the disk of the galaxy, and no star formation is happening in the halo of the galaxy. And in fact, not only is it happening in the disk of the galaxy, it's happening preferentially in the spiral arms. And we look at other spiral galaxies, like this one, this is the Whirlpool galaxy, we can see where the star formation is actually happening. All of these pink spots and red spots that you see are places where where star formation is happening, where it is become, and in fact, it's happened so much that those stars have all turned on and they have heated up their surrounding gas and causing it to glow, which is why you get these red spots here. We call these ionization nebulae because that's what happens. These bright stars, very massive stars, turn on. They emit lots of ionizing radiation. That radiation is absorbed by hydrogen atoms in the surrounding area. They ionize, and then when they unionize, they emit lots of photons, and that's why they glow. Blue stars, we know the blue stars, the bluest stars are the highest mass stars. We know they live very short lives. It's also a measure of youngness of a population if there are lots of blue stars around. And these very dark gas clouds are where the star formation is going to be happening. And they tend to be, as you can see, those tend to be in the spiral arms in particular of this beautiful grand design spiral galaxy. And so you can even sort of, let's go to the interactive figure. Here's M51, same thing. I'll show the labels now. Again, we've got young stars here. You've got dust clouds there where spec stars will start forming. And more ionization nebula down here. And let's zoom in on the young stars. You can see how blue they are. That's how we know they're young. And so if we see the direction of rotation, right, all the stars in this galaxy are rotating, in this case, in a counterclockwise way, and that makes sense, right? Why does that make sense? Well, stars are entering and leaving this density wave. This isn't actually a feature. These spiral arms don't probably spin at the rotation speed of the stars. Stars will come into this region and then leave this region. And these spiral arms can be stationary, they can be moving forward, they can even be moving backwards. Analogous kind of like to a traffic jam, right? Cars come into a traffic jam, they might slow down here for a while as the density gets higher, but then when they leave, they continue moving fast again. We think that these density waves work similar. Just like the actual location of the jam, cars will be moving in and out, the location of the jam can stay in the same place. It can move forward, it can move backward. So that's what's happening here. Stars will enter this. This is where the density gets higher because the stuff's piling up in this high density region. That's where you get stars forming. And then on the other side of that, you get these ionization nebula after the stars are formed. And then a while after that, the ionization is gone and you just have these young stars. And so you can see the star formation itself is kicked off often by material passing through these spiral arms. Okay, let's go back to our slideshow. Okay, so here's some questions for you. You end the class with some questions. On average, which stars do you think are older? Stars in the disk or stars in the halo? I'll let you pause the video and make a guess. Okay, hope you wrote it down. Welcome back. Okay, so again, thinking about which stars are older on average, where is all the present star formation in the galaxy happening? It's happening in the disk. And so all of these, there are young stars and old stars in the disk of the galaxy. The halo has only old stars. On average, the disk stars must be younger than the halo stars. And therefore, the halo stars must be older on average than the disk stars, which is really what I asked here. Okay, that one hopefully wasn't too hard. Here is a harder one. On average, which stars contain more heavy elements at their surface? And by heavy elements, I mean anything heavier than hydrogen and helium. Iron and carbon and oxygen and all of those, gold and tin and all of those heavy elements. Which will have more elements of the surface, disk stars or halo stars? Again, I will let you pause the video, make a guess, and come back. Okay, I warned you that this one was going to be more complicated, and it is. Usually when I ask this in class, somebody will raise their hand and make this argument. Well, it must be halo stars because they are on average older, and therefore they have had more time to fuse heavy elements in their core. That's what the sun is doing, fusing hydrogen to helium. Eventually it will fuse helium to carbon and then go planetary nebula. That is not right. And there's a couple of reasons why. One is that's true, but even for, let's say the sun was turning hydrogen into carbon, all that carbon is hidden. And when I really say at their surface, I mean at their surface, that's all we can really measure directly, right? We can measure the surfaces of these stars because that's where the light that we're getting from these stars is coming from. We can't measure the inside of a star. We don't know without making inferences what the center of a star's composition might be. But we can measure directly the outside of a star. And in the outside of a star, even a sun, even when it's burning, it becomes a red giant and goes to the horizontal branch and starts burning helium into carbon, the surface of the star won't have any more carbon than it did when it started, because all of that carbon is still trapped at the center of that star. But what does happen is the entire galaxy does change in chemical composition over time. You might remember when we were talking about the abundances of elements in stars, at the beginning of the universe, there was only hydrogen and helium, almost nothing else. And so the first generation of stars that formed had to be almost entirely hydrogen and helium and have zero heavy elements anywhere. Now, that generation of stars grows up, they become supernovas. As you know, lots of these heavy elements are synthesized in supernovae. And so the second generation of stars that formed after that first generation of supernovae went off, had a little bit more of these heavy elements in it. And the next generation had a little bit more, and the next generation had a little bit more. And these very old stars in the halo harken back to a time when there was far less heavy elements in the galaxy than there is today. These new stars that are forming in the disk of the galaxy have had the benefit of 14 billion years of stellar evolution and all of these very massive stars that came before it polluting or enriching, if you like, the interstellar matter with these heavy elements. And so stars that are formed today have many more heavy elements than stars that were formed at the beginning of the universe. These old halo stars have very small amounts of heavy elements. And by comparison, the disk stars have a lot more. Here's a quick summary of that. Halo stars, something like 0.02 to 0.2% heavy elements, oxygen, iron, etc. Only old halo stars. Halo stars formed first, and then there aren't many halo stars that are less than, say, 10 billion years. They're all really old. The disk stars then began to form, and all disk stars have an age of less than 10 billion years, roughly. And all of the current star formation is going on in the disk of the galaxy. On average, disk stars have 10 to 100 times more heavy elements and have stars of all age, from very young to very old even. And so that's the rough structure of the Milky Way. I want to introduce a couple of terms at the very end of class here because they're important for the homework. So let me share with you the whiteboard, and I will define these two terms. So astronomers use these to talk about halo stars and disk stars. Population 1, oops, I did a righto. Population 1 stars are disk stars. They tend to be younger and have more heavy elements. Population 2 stars, or just POP2 stars, are halo stars. They tend to be older and have less heavy elements. Okay, that should help for some of the homework this week. And that is where we will stop for today. On Thursday's class, we will come back and we will start talking about how we can measure the mass of the Milky Way galaxy. Okay, see you then.